Recall that this is the gamma function, which is the integral from 0 to infinity with the integrand of t to the k minus 1 times e to the negative t. Here we have a random variable x that has a gamma distribution, and this is the gamma probability density function. In earlier videos, we have found that the expected value of x, or the mean of x, is theta times k. And then we have also found the variance of x, of the random variable x, is theta squared times k. And so for these videos, see the description section for the video links. And now what we want to do is find the moment generating function of x. The moment generating function is defined as m of t, which is the integral from 0 to infinity with the integrand e to the tx times the probability density function. The probability density function again is 1 over theta to the k times gamma k times x to the k minus 1 times e to the minus x over theta. This integral is with respect to x, so this expression here is considered a multiplication constant, so we can move it and place it in front of the integral. E to the tx times e to the x, e to the negative x over theta. It will be e to the tx minus x over theta. So this is m of t. This is the moment generating function. And now let z be the negative of tx minus x over theta. This is tx minus x over theta, which is negative tx plus x over theta. The common denominator is theta. So we have 1 minus t theta over theta. So we end up with 1 minus t theta over theta times x. So z is 1 minus t theta over theta times x. Multiply both sides by the reciprocal of this expression here, then we get x is equal to theta over 1 minus t theta times z. dx dz would be theta over 1 minus t theta. So dx will be theta over 1 minus t theta times dz. For the integrand, we need x to the k minus 1. X is theta over 1 minus t theta times z. Raise both sides to the power of k minus 1. Then we get x to the k minus 1 is equal to theta over 1 minus t theta to the k minus 1 times z to the k minus 1. So in the place of x minus k, x to the k minus 1, we'll replace it with this. This will be tx minus x over theta will be negative z, since z is the negative of this expression. And so tx minus x over theta will be negative z. Z is equal to negative tx minus x over theta, and so tx minus x over theta is equal to negative z. And so that's what we have right here. In the place of x to the k minus 1, we have this. In the place of tx minus x over theta, we have minus z. And recall that dx is theta over 1 minus t theta times dz. This is the same as to the first. So this expression and this expression, the bases are the same. So we can add the exponents. K minus 1 plus 1 is just k. And this expression here, there's no z, so we can move it and place it in front of the integral. So what's left is z to the k minus 1 times z to the negative z dz. Recall that for the gamma function, gamma of k is the integral from 0 to infinity with the integrand t to the k minus 1 times e to the negative t. Here we have z to the k minus 1 times z to the negative z. So this integral here be just gamma of k. So instead of the variable t, we just have the variable z. So this integral here, this is gamma of k. Gamma of k dividing by gamma of k is 1. This expression right here, we can write it as theta to the k times 1 over 1 minus t theta to the k. Theta to the k dividing by theta to the k is 1. And therefore this is the moment generating function. And then we need to find the derivatives, and so let's rewrite this expression here. 1 over 1 minus t theta is the same as 1 over 1 minus t theta to the negative 1. And then negative 1 times k is negative k. The first derivative will be negative k to the front, and then subtract 1 from the exponent, so negative k minus 1, and then the chain rule, using the chain rule, we have to multiply by the derivative of 1 minus t theta with respect to t. 1 minus t theta, the derivative will be negative theta. Negative times negative is positive, so we get k times theta times 1 minus t theta to the negative k minus 1. Now let's do the second derivative. So we have k theta, and again, so we want the derivative of this expression right here. So it would be negative k minus 1 to the front, and then subtract 1, we get negative k minus 2, and then times the derivative of 1 minus t theta, which is negative theta. So this is the second derivative of the moment generating function for the random variable x. And now let's evaluate the first derivative at 0. So in the place of, this is the first derivative, in the place of t, we have 0. 1 minus 0 is just 1. 1 to the negative k minus 1 is just 1, so we get k theta. And recall that this is the expected value of x, or the mean of x. The second derivative, evaluating at 0, so in the place of t here we have 0, 0. 1 minus 0, which is 1, to the negative k minus 2, which is 1. Here we have k theta times theta, which is k theta squared. And then we have negative k minus 1 times this negative right here, which makes it plus, which is positive k plus 1. So this will be just 1. And then this negative here, this negative times negative k minus 1, that will be positive k plus 1. So that's how we end up with k theta squared times k plus 1, which is k squared theta squared plus k theta squared. And so the variance of x will be the second derivative, the moment generating function at 0 minus the first derivative at 0 squared, and we end up with k theta squared. So for the random variable x with the gamma, probability normal density, given with the gamma probability density function, this is the moment generating function. And then all these right here, this just shows how the moment generating function is related to the expected value and the of x and the variance of x.